Hello. Um, the previous lectures we covered linear regression, linear algebra to some extent, and um, we start this lecture by uh, jumping into variable selection. Okay, and the question is, when we have many predictors, um, and we'd like to know which of these predictors or features are associated with the response. Which predictors are associated with the response? In order to answer that question, we need to first answer the question of how many models contain subsets of p variables. So p is something we use to refer to the number of predictors. So when we have p predictors, what are the possibilities? The possibilities are that the first feature is either associated or not associated. The second feature is either associated or not associated. The third feature is either associated or not associated, and so on. So you can think that for any subset of variables, we can have a sequence of 0 and 1s. So we can have a sequence of 0 and 1s with p digits, where each this binary word with p letters, where each letter can be either 0 or 1. Each letter is 0 if the corresponding feature is associated, and it's 0 if it's not associated. So the total number of, and for any of these associations, then we have a model. So essentially we have 2 to the power of p models here available. 2, because this can be active or not active. This one can be associated or not associated. So 2 times 2 times 2, 2 p of them to the power of p. Well, now why do we care about this? Problem is that this is exponential in p. This is for even 30 variables, 2 to the power of p is roughly speaking 10 to the power of 9. That means that if we wanted to test all these models that contain subsets of p variables, so essentially when you have p variables, if we wanted to consider all the possible combinations of these variables, it'd be impossible to test. Computationally, it's impossible. We cannot look at every combination of variables and predictors. In theory we can, but the number of possibilities is so big that the computational power needed to analyze a problem that is a decent size, like 30 variables, may take days, weeks, or days or weeks. You can test that. So the bottom line is that when we want to find predictors associated with the response, there are many, many, many possibilities. And we cannot look at all of them. So these are the 2 take-home messages so far. Why would we want to look at all of them? We wanted to look at all of them so we can fit a regression model and then test it and then say, okay, among all these possibilities, this regression model is the best. That's why we want to do it. But we can't do that. So a lot of people for a long time have been thinking about efficient and automated approaches to choosing a smaller set of models or smaller set of predictors. One of the first approaches is the forward selection approach. It starts with the null model. What it means by a null model is a model that has only an intercept. So it's a constant model, no predictor, constant, only intercept. Then, in the next step, it creates a list of all the p predictors, and one by one, it will fit a simple linear regression model with only that feature. So that will lead to fit p simple linear regression models. And for any of these fits, it can look at the corresponding p-value of that variable. So then for every predictor, we have a p-value. And then it will add to whatever the current model is, that predictor with the lowest p-value. That's one way of going. Another way is just to pick the model which leads to the smallest residual sum of squares. So that's also depends. There's no standard way, so there are different criteria. So residual sum of squares is one measure of fitness. P-value is another measure for how significant the predictor is. And then we continue that. We add these features until some stopping rule is satisfied. Okay, and the stopping rule is saying, okay, when the lowest p-value is greater than 0.1 or 0.05, for example. So it's an iterative process. This is an iterative process. And it's a greedy process. And in greedy methods, a problem that can occur is error propagation. And what we mean by error propagation is that when you start with a null model and then you want to find that one predictor which captures as much as possible variability in the response, yes, you find something, and that association might be strong. But that's probably the best predictor if we only we're considering models with one predictor. But if we at the end of the forward selection, we are looking at models which have typically significantly many more predictors than one, and then we are talking about combinations of predictors that are supposed to capture the variability in the data. And when we are talking about the combination, then that predictor that we picked in the first step might not be a good predictor with any combination of other remaining predictors. So that's what we call error propagation. The first steps, we add greedily these predictors which have a high correlation, and then later on we may realize that, oh, all these predictors that we picked along the line, along the road, they already can capture what the first predictor was trying to say, so maybe we don't need that. But the forward selection method does not have any way of dealing with this problem. So, forward selection, start with no variable, iteratively add the variable that results in the lowest residual sum of square or the highest p-value. And then you can continue until some stopping rule is satisfied. Sometimes it's AIC, BIC, adjusted R square. These three measures, we'll see them later again, but these three measures, they, and any model that is more complex will obviously have a lower residual sum of squares. So that's a little bit misleading. That's a little bit optimistic. Any model that has more predictors will lead to smaller residual sum of squares. How can we account for the fact that more complex models will underestimate the test error? So the training error is hugely optimistic. So AIC, BIC, and adjusted R squares are ways to account for the model complexity. Okay, so you can think of them as some sort of measures related to the test error. Okay, they're not always perfect, but their idea was to try to find something that is directly related to the test error, and it's different, something that's very different from the training error. Okay, it's something that a measure that takes complexity into account. Okay, so that's forward selection. Excuse me. Okay, so I'm trying to find the forward selection part of in the book. Okay. So it's in page 78 of the ISLR book. I suggest you read this. I mean, I covered the main topics that I'm covering, but just as a point of reference, in case you wanted to know where in the book to look at. Now, another method is the backward selection method. The backward selection starts with the full model, meaning that it tries to find a regression model that includes all the variables. Well, that creates a problem, right? Because if the number of variables is larger than the number of predictors, then you can't use the forward. You can't include all those variables. Okay. So, but anyway, let's imagine that the number of variables is not larger than the number of predictors. Okay. Then the backward selection starts with the full model, essentially all the variables in the model. Then it starts removing variables. And the way it does it, it just looks at all the variables and it just removes the variable with the largest p-value. So in other words, the variable, the statistically the least significant one. And then it will refit the remaining model with the model, the linear regression, with the remaining predictors. And then it will remove the variable with the largest p-value again, and then it will refit them all with p minus 2 remaining variables, and it will just continue this until some threshold. So this is backward selection, and as we said, it cannot be used if the number of predictors is larger than the number of observations. Okay. And then we have mixed selection, where it's a combination of backward or forward. So we typically it's the way it is that we add the predictors to the very end and then we start removing them. The hope is that by at the end, if we made a mistake at the beginning, those mistakes at the end will have a large p-value, so by doing a backward selection we can just get rid of them. Okay, so this is we talked about backward selection, we talked about mixed selection. So the next thing I want to do is I want to go over an R example. Okay. So in this example, we go over the Boston data set. We use the Boston data set. What is the Boston data set? We go to the packages. We go to mass and housing values in suburbs of Boston. So we have 500 observations, 14 predictors, and the predictors are crime per capita crime rate, proportion of residential land zoned for lots over 25,000 square feet, and proportion of non-retail business acres per town, the relationship of the neighborhood with the Charles River, nitrogen oxides concentration, average number of rooms, proportion of owner occupied. Okay, so then we have the 5 employment centers, and then we have this measured distance, which is a weighted mean of distances. So it's essentially maybe the house value will be negatively associated with distance. I don't know, maybe not. Index of accessibility to radial highways, full value tax property rate per 10,000, and I mean you can look at these. Here are the 2 papers which use these. Anyway, this is just an example. You can use any data set. And here we are fitting the median value. We are regressing it against everything else in this data. And then we're creating a least square fit function. So And then we just capture the formula because we're going to use it later. But here's this. Let's look at the summary of fit. So the R square is 0.74. Adjusted R square takes into account the number of predictors. So it's an R square that also depends on how many predictors we have. It gets smaller as the number of predictors get larger in comparison to the R square. But anyway, let's look at these. For example, crime per capita. Well, crime per capita decreases. Proportion of residential land, I don't understand this relationship. Proportion of non-retail business acres per town. I don't understand that either. Nitrogen oxides concentration. The larger this gets, the more the median value decreases. Distance. The more distance to 5 Boston employment centers, the more the median value decreases. And anyway, now age and industry are not significant, as we can see. Okay, but this is pretty straightforward stuff. Now we can also fit a model with no variable. Essentially, we're just fitting it with an intercept, right? And before I do that, I wanted to show what is all terms form. That's as formula. So it's just a formula. But now let's move on to the null model. It's a model which has no predictors. Okay. And yeah, this is what we get essentially. Just an intercept, which is going to be the mean of the, if I'm not mistaken, of the values. So it will be mean Boston yes, so you see the mean response, if you fit the intercept, it's just the mean response will become the intercept. Okay. And anyway, now why did we do this? Because I wanted to illustrate how forward-backward might be implemented in R using this code stepper R. Essentially, when you run this, you're calling all the functions that are available in this function written. It's courtesy of Professor Teravainen, who teaches an R class this semester. Okay. So this file, this is stepper R, has 3 functions. Enter terms, so it's from here to here, which is about entering terms. So you start from the null model, you start from a model which has no predictors, and then you add terms. This is a step that is used in the forward selection part. We'll get to it. And then we have exit terms, which is a function which removes predictors. This will be called in the backward the backward selection steps. And then here we have the main function, which is manipulate terms, that is called here. Here we're saying manipulate terms. We give it the null model. We give it all the terms, the formula, the data, and then we give it two thresholds. Okay, and the total number of iterations. So let's look into this. I just will go over it at a very high level. So we have the function. The function receives a model. What is a model? A model is this linear regression object, fit, whatever. Okay, so it's a linear regression fit. It's at the beginning, it's the null model. Then we have all the terms, the data, and then we have the entering threshold for the p-value. We have the exit threshold for the p-value, and these are the values that these are going to be the default values if they are not provided here, but here they are provided, so they will be over written by these three numbers. Okay, so since this is an iterative process, we always have a previous model, and then we have a old model, and then we have a new model, and so we have to at least keep track of the previous model. And at the beginning, the previous model, there is no previous model, it's a null model. Okay, now and here we check that if the entering threshold is greater than the exit threshold, then here we're getting a warning. But here's what's really starting. Okay, for as many iterations given, this is what we do. First, we print the iteration number. Then the old model we assign null. The current model becomes the previous model. And then if the old model, here we have a while loop, okay, which when we enter it, what happens? We take the old model, right, which is null, get the coefficients, we sort them, and see whether this is equal to the coefficients of the model we have. In the beginning, the null and the model are obviously not the same, so they are not identical. So the negative of it, which is this sign, makes it true. So we get into this while loop. A dot will be printed each time we go one time around in this while loop. The old model, the current model, will be saved as the. Let's just remove these. These are good for debugging. So whatever model we have, we put it into old model. Then we call enter terms. Enter terms will receive the model we have, all the terms, the data, and the entering threshold. And what it does is it adds a feature. This function to whatever model this is, whatever predictors it has, it will look into all these terms that are not into this model, and it will check the p-value of every single of them, and the smallest one that passes this threshold will be added to this model, and then we call this the model. And then we have the model, and then we have the old model. Okay, so in this stage, this line is add to the model the variable that has the lowest p-value, for example. That's what that line is doing. Okay. Now I will get to this function up there, but for now, let's just stay here. I want to go over the manipulate function completely before going to this other sub functions. Okay, so let's just, we don't need these. Okay. Okay. So at some point, right, this entering terms won't add any new term among these terms, either because we reached all the terms or there is no predictor that passes this threshold. So the old model and the new model will be the same, and at that point they will be identical based on the coefficients, and then we will just, at this point, it is at this point where we won't go through this while loop again, and then we will just reset the old model. Okay, so this part is the forward forward selection part. Okay. Now here we have the backward selection part, where again we have the old model and the old model is null, so they are not identical, so we enter this while loop. Model will get into the old model, and then we exit. Again, we look into this model and we look at all the predictors, and this function finds that predictor that by removing it, the model, the predictor with the highest p-value, essentially. That's what it's doing. And it places it into model. And if in doing this, the model doesn't change, if it doesn't change, then model will be the same as old model. They will be identical, and then we will exit this this loop. Okay. And then we have previous model and model, which previous model is the model we start with at the beginning of the forward selection, before we do the forward selection. But now here we are seeing if the forward and the backward selection doesn't lead to any change. So if the model that we had here is after the forward selection, okay, this is what I should call forward selection, and then after forward and backward selection, if the model hasn't changed, then maybe we should just stop, because we reached something like a local minimum, so we're just breaking out. Okay. So this is a very high level view at forward backward selection coding. Now we can look at the inner workings of each of these. Add to the model the variable that results in the lowest p-value, or remove the variable with the largest p-value. Okay, so let's look at this. Enter terms, which happens in the heart of the forward selection. Enter terms. Enter terms receives a model, receives all the terms, which terms is this is all the terms and the data. Okay, so in this part we get all the variables, all the predictors, right, from this model. We put them all wires, and then we remove the first one to remove the response. So essentially, old TS is a list of the terms that are currently in this model. All the list of all the predictors that are currently in this model. Okay. And then we use the add one function, which essentially what it does is it takes the current model, so when it has the model, it has also all the predictors involved. Then it looks at the list of predictors given here, and anything that's here, but it's not used already in the model, will be one by one added to this model, and then the p-value and the residual sum of scores and everything will be placed into M. So M is a matrix, is something like a matrix where each row corresponds to one of the predictors in all terms that's not used in model. And one of the columns of this matrix is the p-value. So here we sort the p-values from smallest to largest. Then we look at the smallest one, right? We look at the smallest one. And then if the smallest one is less than the entering threshold, then we say, okay, here are the old predictors. Take the name of that candidate predictor, together make it the new name of the predictors. Okay, and if the threshold, if it doesn't pass the threshold, just return this model. None is significant, return old model untouched, and that's that. Once we have a new list of predictors, here we use this command which takes the all vars 1. What is all vars 1? All vars 1 was what we removed here, and it's the response. So take the response. Here we're creating a text. Take the response, take these predictors, put between this plus, and then separate the predictors where there are pluses in between with this tilde from the response, and that will be the formula. And then using this data, turn this into a formula, do a linear regression fit, and then that's what will be returned. Okay, so let me just spend a second about this line, which is just something that you can hear. Maybe no, not this one. Okay, this might be useful. So something that we've been doing here a lot is to create a formula from a string, and this occurs in functions where the formula arguments are passed in as strings, which is happening what we're doing here. So if you just write this, you will get the string, but if you put it into as formula, it'll be a formula that can be given to a linear regression function. This is what we did actually. This is what we did. Remember, this variable is y, and we want it to be separated by this tilde, which goes in here. And then we have this group of variables, which is x1 to x3. We want them to be separated by the pluses. And then we have the formula. That's what we're doing here. Okay. So the forward selection part calls this function, and we enter. The backward selection part calls the function exit terms. Now exit term again starts with a model. It's probably the full model, or it's the model that we receive at the end of the forward selection, and a threshold for dropping out or kicking out variables. So here we take all the variables in this current model. We remove the response, so we get a list, a vector full of the name of the predictors used in the current model. We look at the coefficients. We remove the intercept, and so here in this M, we have a summary of all the coefficients except for the intercept, right? And that summary will also include p-values. Okay. Now, here we take the column, which is labeled as this probability. It's a column with the p-values. We sort it from smallest to largest, right? And sorry, largest to smallest. And the reason is that we want to find the largest, so that we probably remove it. If the largest is greater, the largest is the first one, greater than our threshold, then remove it. Remove the worst predictor and put it here in this list. And then otherwise, then there's nothing we need to do. We return what we have, and then that means we're done. But if we're not done, here we're creating this formula again that I just described, and using this formula, which is all the variables we had. This is the response, and these are the names of the new predictors, which are separated by plus, and then this whole variables, predictors that are put together with the plus are separated with the tilde from the response. And this will be the formula. The formula will be given to the linear regression function to use it to fit this data. And the result will be returned. That's what's happening in backward selection. Okay. Let's try to use this. So we start with the null model. We give all the terms, data, the entering threshold should be 5%. The entrance should be, exit should be 10. 0.1. So what this means is that we will add in the forward process, we're saying essentially add variables, as many variables up to the point where there is no variable to add which has a p-value less than 5.05. That's what this means. And this 0.1 means that once you reach the forward selection, the end of it, remove variables, remove the one with the largest p-value, but do that for until there is no variable left that has a p-value greater than 0.1. So I just run it and then can look at it. So, okay. So it starts with the intercept and then it adds lstat. RM, PT ratio, distance, Knox. So here we can see the order in which the predictors are added, monitor that, but what we like to look at the end is the summary. And at the end, these are the variables selected. You see all of them are significant, and you can compare it to summary of the linear regression model. some variables are removed. Among them, indus, age, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. So 2 of them were removed. Here, the 2 happen to be the ones that were initially not significant, and that's just by chance, actually. In a lot of cases, variables might be removed that are significant here, but there might be added here that are not significant here. So this is just a coincidence that the variables that are removed happen to be those that were initially not significant. Okay. Now, what I want to draw your attention to is the R squared. R squared for the full model is 0.7406. For the reduced model with smaller number of variables, it's also 0.7406, which may mean that these two models have fit the data equally well, but this model has 2 variables less. So how can we take that into account? And adjusted R square takes that into account. Adjusted R square takes the number of variables into account, and the adjusted R square for this one is 0.7348, and for this one is 0.7338. So the adjusted R square for the smaller model is actually larger, which is evidence against this. So just another way of looking at this. Okay. But this was an illustration of how to do backward and forward, and also it was a high-level illustration of how forward-backward can be implemented thanks to this code written by Professor Trevanin. And what is useful here to note is that this format here can be extended to different models. So LM here can be replaced with logistic regression or any other regression type that you're looking at. So backward and forward additions, this procedure can be implemented not just in linear regression, in any other type of regression.